This is the first of 3 lectures from Chapter 9. And Chapter 9 is all about chemical bonding. And so this first lecture will be focusing on ionic bonding. Just some basic vocabulary to begin with. A chemical bond, and that's any chemical bond, not just an ionic bond, is an electrostatic attraction between two atoms. What do I mean by electrostatic attraction? That means attraction between opposite charges. Okay? So it's pretty easy to see what the electrostatic attraction is when you have an ionic bond. It's between the cation and the anion, right? It's a little bit trickier to understand the electrostatic attraction that's involved in a covalent bond, and we'll go over that later. But I do want you to know that every single chemical bond is not really a physical entity, but a strong electrostatic attraction. Atoms bond, the driving force for atoms bonding is lowering of energy. It's a driving force for most of what happens in nature. And this is kind of a visual, it's a potential energy diagram, which you should be able to interpret. It shows the individual atoms far enough away from each other to not feel each other. We call that zero energy. As the atoms approach each other, in other words, let me scooch that up a little bit. As the internuclear distance, as the distance between them decreases, you can see the energy going down, which means it's stable. It's a stabilizing force as the atoms are approaching each other and feeling the attraction to each other. It reaches a point at some distance, some precise distance, where it's the lowest in energy that it can be. And at that point, we call it a chemical bond. So the lowest energy point on a potential energy diagram, if you were to extrapolate down to the x-axis, you could find the bond length of a particular bond. And if you extrapolated the lowest energy over to the y-axis, you could find the bond energy of that particular bond. And so be able to interpret this, and I guess the most important thing to remember is go to the lowest energy point and take the readings at that point. Do that. So the 3 types of bonds that we'll be talking about are ionic bonds, and just kind of a review for you. You may remember that from high school chemistry. Ionic bonds are between a metal and a nonmetal. So one element from the left of the stair step and one from the right side of the stair step make ionic bonds. And an ionic bond involves a full transfer of valence electrons from the metal to the nonmetal. Covalent bonds occur between 2 nonmetals, that is 2 elements that are on the right side of the periodic table. There is no electron transfer in covalent bonds. The valence electrons are shared in between the 2 atoms. And then we're really not going to spend much time, if any, on metallic bonds, but I want you to be aware that metals, when you have a bunch of metal atoms together, they're considered to actually participate in metallic bonding. And basically, if you hopefully remember your ionization energy trends, metals have low ionization energy. That means their valence electrons are loosely held. And so when you have only metals present, just think of aluminum foil or iron, any type of metal, what happens is all of the valence electrons kind of tend to associate with one another, and they call it a sea of electrons, leaving behind the rest of the atom, which would kind of end up with a positive charge. And that's kind of how metals tend to exist, and it ends up creating an electrostatic attraction that is considered a bond. Think of as, I did not mean. All right, so I'm going to kind of work in reverse. These are just graphic depictions of the different types of bonds. So let's look at metallic bonding first, and that's the one that has a sea of electrons. And so think of the metal atoms as the gray spheres, and their valence electrons represented by the red dots. And so the valence electrons are loosely held, so they're kind of not as close to the atoms as they might be for something with a higher ionization energy. So it kind of looks like a bunch of cations surrounded by loosely held valence electrons. Ionic compounds, and rather than being like a single entity, like rather than having NaCl be a unit that you could actually pluck out by itself, because of the fully developed charges on ionic compounds, cations and anions, you end up with this large three-dimensional glob, not a glob, actually a very precisely arranged crystal of cations and anions. And because of that, ionically bonded compounds are always solids, they're always crystal shaped, and they share a lot of other similar properties because of this very unique structure they make. Covalent bonding, on the other hand, can take on a lot of different forms. Rather than always being a solid and a crystal like ionic, covalently bonded molecules can be liquid, solid, or gas. And they do not transfer electrons, they simply share them. So you end up with discrete individual molecules. So if you're looking at H2O, you don't have this big three-dimensional array like you do with ionic. You can actually have individual H2O molecules swimming around. Alrighty, so let's now focus on ionic bonding for the rest of the lecture. Ionic bonding, again, involves a full transfer of valence electrons from the metal to the nonmetal. And so let's imagine we're making potassium chloride. So we're going to start with a potassium atom and a chlorine atom, neutral to begin with. Potassium's in group 1A, so it has one valence electron. It has a low ionization energy, as do all metals, and so it's pretty easy for potassium to give up its one valence electron and become a cation. That's the first step. Well, that electron's got to go someplace. Where does it go? It's going to go to an atom that wants extra electrons. In other words, an atom that has a high electronegativity. And the halogens are perfect for that. In group 7A, their electronegativity is high. They will readily accept extra electrons to become anions. Now you have a match made in heaven. You have a positively charged cation, negatively charged anion, a very strong electrostatic attraction between them, and we now have an ionic bond. Since it is the valence electrons, or are the valence electrons that create chemical bonds, I wanted to remind you or refresh your memory about how to figure out how many valence electrons each element has. So if you've gotten rusty in this, you'll want to make a note to commit it to memory. The number of valence electrons matches the group number on the periodic table. So group 1A has one valence, group 2A all have two valence, group 3A have three, and on to group 8A, the noble gases, have 8, except of course helium, which is an exception and has a full outer shell with only 2. So make sure you know the number of valence electrons because that'll tell you the number of electrons it has to contribute to making chemical bonds. One of the theories that was developed and is really handy when talking about chemical bonding is the Lewis theory. And the Lewis theory simply uses dots to represent valence electrons. So let's look at an example of that. For example, if I were to draw the Lewis dot structure for the element oxygen, or for the atom oxygen, oxygen is in group 6A, so it has 6 valence electrons. So a Lewis dot structure for oxygen would show those 6 valence electrons spread on the 4 sides around the symbol for oxygen. Now, one thing to keep in mind is when you're placing these dots or valence electrons around the symbol, you want to place one dot or one electron on each side, each of the 4 sides, before you pair any of them up. So kind of like Hund's rule. So now once you have one on each of the four sides, then you can start pairing them up. So again, oxygen being in group 6A has 6 valence electrons, and so this would be the correct Lewis dot structure for the atom oxygen. And here, just to show you the Lewis structures of all of the common elements, I left out the transition metals. But I want you to look at each group or family and notice the pattern. You can see very easily by glancing that every element in the same family, now hopefully you know the vocabulary that one of these vertical columns are called either a family or a group. The elements in the same group or family have the same number of valence electrons. And that's why the properties for the elements in the same family or group are very similar. The number of valence electrons affect the chemical reactivity and many other properties of an element. All right, so to show you kind of pictorially what happens when you make an ionic bond, let's look at a Bohr model of sodium. Okay. Sodium has an atomic number of 11. It's in group 1A, which means it only has one valence electron in the third energy level. And then let's look at fluorine, which has 7 valence electrons. See, 2, 4, 6, 7. And all atoms strive to have a full outer shell, which means 8 valence electrons. So if you look at sodium, the easiest way sodium can get a full outer shell would be to lose this one valence electron it has. By doing so, it ends up with the undershell, the shell that was under that, completely full. So that's why sodium wants to get rid of that one valence electron. Fluorine, on the other hand, to gain 8, it's only one away from 8, so it would like to steal an electron from another atom, because by doing so it would have 8 valence electrons in a full outer shell. To look at it more from, rather than a pictorial view, from electron configuration view, if we were to draw out the electron configuration of potassium, of course we can see it has one valence electron. But if it loses that one valence electron, the undershell, which is energy level 3, is then full. It has 8 electrons, 2 plus 6. And so, again, potassium and all elements in group 1A will quite easily lose their one valence electron. All right, so probably the way that I would ask you to show bonding, ionic bonding, on your test is using the Lewis dot structures. So I would like you to pay extra close attention to this slide and make sure that you can do something like this for the test. So if I told you sodium and chlorine were bonding, and to show with Lewis dot structures how that occurs, this is what I would want you to show. The neutral atoms with their valence electrons before any bonding occurs. Then typically chemists will use arrows to show the movement of electrons. And so we know that sodium donates its one electron, so we show that with an arrow. And then show a line, meaning chemical reaction, right, yields. And what you end up with then is the sodium cation and the chloride anion. Now here's an important thing to remember. All cations with Lewis dot structures are shown with no dots. I call it naked cations. So notice that the sodium is put in brackets and the positive sign to show that it's lost an electron. And now the anions, the negatively charged result of electron transfer, always shows 8 valence electrons to show that it's gained an electron. And again, both of them tend to be put in brackets. Don't forget the charges. And remember, cations are naked and anions show all 8 valence electrons. The sign to show its charge. I mentioned at the beginning of this lecture that all ionically bonded compounds make crystalline solids. And we call this structure, this three-dimensional structure of cations and anions that are attracted to one another, a crystal lattice. We also talk about lattice energy. So I've mentioned before there are electrostatic attractions that hold the cations and anions together. And so if you have a cation and an anion, the energy that is given out when those two come together is called lattice energy. The textbook definition of lattice energy is the energy released when an ionic solid crystal forms as the separate ions come together. So look at the pictorial here. In our example, sodium chloride, the anion is chloride, the cation is sodium. So think of them apart. As they come together, there's going to be energy released as they go to a lower energy state. And that energy released is called the lattice energy. So there are a couple of obvious things that affect the size of the lattice energy. Primarily how large the charge is on the cation and anion, and also the distance between the cation and anion. So Coulomb's law is what we use to calculate the level of attraction that two charged particles have for each other. I'm not going to have you do calculations using Coulomb's law, but I do want you to be familiar with it so that you can see the variables that affect the lattice energy or the level of attraction. So Q represents the charge on the ion. So if we were talking about the sodium cation, Q would be +1 because sodium has a +1 charge. The higher the charge on the ions, the stronger the attraction and stronger the lattice energy. So for comparison, if we were talking about the magnesium cation, which has a charge of +2, because magnesium is in group 2A, magnesium would make ionic compounds with a stronger lattice energy because there'd be stronger attraction to the highly charged magnesium ion. Now, also, the size, which is R is the radius or the distance between the two ions. As R gets larger, as the distance between the two ions increases, lattice energy decreases. They are inversely. That makes sense, right? If you have two things that attract each other and they get really, really far away, they're not going to feel that force of attraction very much. But if they can get really close, they're going to feel that force of attraction quite a bit more. So the charge on the ions is number one, most important. But if the charges are equal, then you look at the distance between the ions. So let's look at these two examples. Sodium and fluorine. Sodium, let's say, would represent Q1, which would simply be +1. Fluorine would represent Q2, which is simply -1. So each one of these ions has an absolute value of charge of 1. And obviously 1 times 1 is 1. So the whole numerator part of Coulomb's law would be 1. Let's look at calcium oxide for comparison. Q1 would be +2, Q2 would be -2, 2 times 2 is 4. We're not going to worry about the net charges at the end. So you would expect the force of attraction, the lattice energy for calcium oxide, to be about 4 times higher or stronger than that of sodium fluoride. It's a bit trickier to look at the distance between two ions and its effect on lattice energy. You really only need to do that if the charges, if the Q values on the ions are equal to one another, as they are here, okay? In this case, all the cations and all the anions have a charge of 1. So if that's the case, you must look at the distance between the ions. And clearly, the smaller the ion, the closer it can get to the other ion, okay? So to minimize distance, you want smaller ions. So of these four pairs, which pair probably has the smallest R value, in other words, the closest to each other? That would be lithium chloride, because lithium is the smallest ion. And so if you look at the actual lattice energies for each of these, you can see that the, whoopie daisy, you can see that the lattice energy for lithium chloride is the largest of the other ones, simply because the distance R in the denominator of Coulomb's law is smallest. Now, all lattice energies are going to be negative, because lattice energies are always negative, which simply means as the ions are attracting each other, they're giving off extra energy, going to a lower energy state. So if you look at a chart of lattice energies, hopefully they make sense. Here's ones with lithium ions, and you can see the lattice energy is decreasing as we go to a larger and larger anion. And then we jump to sodium. Sodium itself is larger than lithium, so that R value in the denominator is going to get a little larger. You would expect the lattice energies to go down. They do. As we go over to the second column, we're going to charges of +2 instead of +1. So you would expect lattice energy to increase, and it does by quite a bit. Here's some for you to try to make sure you've understood this last several slides. So I would recommend turning off this lecture, making sure that you can guess which one of the ones has a larger lattice energy, and also be able to explain it concisely. And then I'll go over the answers on the next slide. All right, so I'm going to go ahead and go through the answers. If you're comparing sodium chloride and potassium chloride, in the case of A, sodium chloride, potassium chloride all have a charge of +1 or -1, so the charges are the same. So this is a case where you need to look at the relative sizes. Now, if you compare the size of sodium, ooh, man, that's not looking so good. If you compare the size of sodium to potassium, you'll see that potassium is quite a bit larger than sodium. It's farther down in group 1A on the periodic table. And so the R value will be smaller for sodium. It'll be able to get closer to the chloride than the potassium. And because of that, sodium chloride will have the larger lattice energy. All right, so B, again, they all have the same charge, and so we have to look at sizes again. Obviously, since they both have sodium, that's not going to be a factor. So now you need to look at the sizes of the anions, fluoride versus chlorine. That is my dog drinking water, by the way, not me. All right, so again, you always want to look for the smaller ion. The smaller ion is going to be able to get closer to the other ion and have a stronger attraction. Fluorine is smaller than chlorine, so sodium fluoride will have the stronger lattice enthalpy. Looking at C, now your charges are different. Magnesium has a charge of +2, sodium has a charge of only +1. The higher the charge, the stronger the lattice energy, so magnesium chloride is the strongest. Comparing D. Magnesium has a charge of +2. Oxygen has a charge as an ion of -2. So the total Coulombic attraction for magnesium oxide would be 4. On the other hand, magnesium chloride, although magnesium has a charge of +2, chlorine has a charge of only -1. It doesn't matter how many of them there are. You're only talking about 2 atoms at a time. So the Coulombic attraction between magnesium and chlorine is only 2. So magnesium oxide has a stronger lattice energy. And here we go, the last slide in this first lecture. are the unique properties that ionically bonded compounds have. And what I usually remind my students or ask my students to do if they're asked a question about properties for ionic compounds, to think of table salt. Table salt's very representative of all ionic compounds. Ionic compounds, first of all, are always solids, and they are always crystals. And that's because they're made up of ions that arrange in a very particular way to maximize the attraction, and that real particular way of arranging themselves results in these beautiful crystals. They tend to be hard because they're crystalline, so they're kind of hard to smush. And again, because of the very strong attraction between ions, they have high melting points. They're hard to kind of break apart and melt or boil. And finally, the liquid or aqueous state of ionic compounds conducts electricity. So we can talk more about that a bit later, but basically electricity is the flow of electrons. And in order to allow electrons to flow, you need other charged particles to kind of push, pull, move the electrons around. And so a solid ionic compound will not conduct electricity because the ions are not free to move. But if you melt it, it's called molten ionic. If you melt it or dissolve it in water, then it does conduct electricity. That might be good for multiple choice questions. So that's it for lecture 1.